Hi everyone, thank you for showing up for this talk. My name is Huiling Liao and I'm come from Department of Applied Maths, IIT. And today I'm going to talk about the efficient region of interest detection through sequential decision making. So basically the motivation for this problem start with some circuit design from some engineering problem. Basically, right now we all have lots of like laptops, phones, and everything electronic device. So we need to design certain chips to make it be able to do all the functions we want it to be. But there are usually lots of attributes, lots of features we want to achieve, and there are tons of parameters we need to consider. But in reality, we don't actually know their relationships, right? So it will be really hard. It's like propose a statistical model. We can propose tons of models, but we need to know whether it works or not, whether it can achieve certain behavior we want or not. So that's when we are actually consider the problem. Does the proposed design do what what is intended? So we don't really focus on the design part. It's more from a verification part for a certain design. And so some motivation in summary, it's we are going to consider the configurations with extremely low failure rate, which means if we want the phone to be more, let's say, energy efficient. So we have some matrix to evaluate the efficiency of the phone. And if certain performance cannot achieve the ideal or some threshold of this matrix we set it to be, then we said, okay, it's failed. So we are considering the configurations where this kind of failure happened for different kind of matrix with its designed. And because it's very rare, which means if you use grid search or random sampling, it's very likely you cannot observe any failure. But it doesn't mean it doesn't exist. It just means the space is way too big. And if you only put down a few points, these rare regions may not show up in your observations. So the difficulties mainly come from the large number of variables or attributes we are considered. And also, we don't really know the relationship between the parameters and their effect on the performance we are interested in. And also, it can be very computationally expensive if you're trying to design a circuit or design the chips. And before it goes to the production part, you need to verify the performance before like a large amount of products go to be sold. So it will be really hard if you come up with like hundreds of design and each of them needs some verifications. It will be expensive to do that in reality. So that's the computational expensive or expensive in real life. Also, what we want is we want a very stable design, which means whenever we use this kind of product, it can achieve certain performance levels we want it to be. So the ideal case is everything is perfect. Everything does their job perfectly and there's no failure at all. Or we can slightly lower the requirement, but we still want it to be relatively stable or achieve certain performance. And there are some methods for failure rate estimation right now, but most of them usually have some very hard assumptions to achieve actually when you do the research or when you're trying to actually do the verification. And lots of them based on these two assumptions is the first one is the region of the failure is somehow known. We have some kind of experts or experience or knowledge about the regions where it's most likely to fail. Or in lots of papers, they also assume we observe both success and failures in our data sets. Or even if we just have one or two failures, we still have some kind of information in this case. So when the failure rate is actually extremely rare, this detection part where we can actually observe the failures become hard. So the detection itself becomes a much more fundamental problem than directly estimating the failure rate. So that's why we focus on the verification or the region of interest or the failure rate, failure detection in this case. So let's consider a more simple case. We are trying to do a hide and seek game here. And you can do this game in your bedroom, in your house, or you can do it in Disneyland, let's say. And the budget limit we are interested in is actually like the time limit for this game. So, and what we are trying to do is we must find all the hiders before the time runs out. So it means we cannot explore every space in a very large park, right? Let's think like a Disneyland. There's no way you can go to all the corners of the Disneyland in like 2 hours. Which means if we only have a naive seeker or like a random sampling kind of design, it's like we just want to we just go to some random spots and hope for the best, hope for luck. And a strategic seeker or a smarter seeker, they will do something different. We are trying to follow some clues the players left behind. So it can be some like the pattern of the footprints, or they leave something on when they are trying to run somewhere, right? So this kind of information can help us narrow down the area we're going to search. And another crucial condition for this case is these hiders may hide in very different corners. And knowing the location of one may not give us lots of information about where the other one is. So this is like when you consider a multi-model function or a more complicated function. And our goal is to find these disjoint regions where each of them have the points satisfy certain performance. Finding one, it's more like the global search, right? Global optimization. We're trying to find the one with the lowest or the highest optimal in our scenario. That's like finding only one. But if we are trying to go further, it's like we're trying to analyze what kind of combination of the attributes can lead to the failure, or what kind of relationship they are contributing to the overall performance. Then we cannot just stay at one spot. We don't care the global optimum that much. We care about if we can find these kind of disjoint regions, and if we can find them, we can figure out a way to study the relationship. Only focus on the points within these regions to see their relationship with the performance we are interested in. So that's why we are trying to do something like the strategic search. So the setting here, we are going to consider this design parameter space and like the hyperparameters for neural network, like when we are trying to do hyperparameter tuning, or some kind of drug design, we're trying to figure out what's the proportion relationship between different components, or different kind of designs. And for each of these configuration X, a simulator can compute some performance value, any performance value, like the Y. And it's a function of the X. And it can be noisy, which means we may not observe the true value. It's a noisy version of the value. And we assume it's a black box function, or it can be something parametric but super complicated, which means you can like evaluate the thing, but you cannot like write down the function directly sometimes. So that's why we consider it as a black box function. So what we described before, the hide and seek and the park, is like the parameter space. The hider is the failure points. And the region where contain the hider and they're destroying is like the, we call it failure regions, or the region of interest in our case. And when we say we're going to track some spot, it's like we're going to evaluate it. And once we get some information, we can do some model update. Like we accumulate more knowledge about where those hiders are. And the time limit is the budget here. And so in this kind of scenario, why the random sampling fails, it's probably pretty intuitive, right? Because if we consider some failure rate pretty low, like 10 to the power of -4, and after collecting 400 points, and they're select uniformly at random, and the probability of there contains at least one failure, it's only lower than like 4%. And if you want a higher observation rate for this one, it probably means you need, or if you need to achieve certain number of failure observations, you need to select more points given this 10 to the -4 failure rate. And if you make it like even more rare, 10 to the -6, 10 to the -8, then it means you will need to get roughly 10 to the 6 samples to have approximately 50% chance of finding a single failure. So in real life, it will mean it will be a very expensive scenario. And each evaluation will cost another bunch of money and things like that. So we don't want to do this. We want to have some energy or cost efficient way to do it. So not just this random sampling is inefficient but also they may be inadequate. So what we are trying to do is we're trying to think about a way to guide the search based on the information we have collected so far. Like what we mentioned, a smart agent would do. So basically, it has this stage for this kind of modeling. It's like given some observation, given some data we already collected, it can be very few data points, like 2 or 3 data points. We can start with that as well. It will be very bad estimation or we get at the start, but we will keep improving the model. So there will be some initial design, and then we move on to build a model. And basically in this part, it's like what kind of model, what kind of belief we want to put in the model for this data or for this specific pattern we are trying to figure out. And then we need to ask the question is, okay, given this thing in hand, where should we do the evaluation next? Which point can give us more information regarding the overall goal we are trying to achieve, right? And then this will help us to design where to do the next evaluation. And then we can actually do the evaluation and include the data point to our modeling and update the model and do it over again until it achieves some stopping criterion or achieve the budget limit. And ideally, it's like we can show some finite sample convergence or theoretical results for this kind of performance, right? So The reason why it's important is because this goal cannot achieve in one step. And also, what we are trying to do is like a sequential design. So we can slowly approach the regions we're interested in. And then we're trying to maintain some belief, and which can also be updated using the newly collected data. And then we are facing some resource constraints. That's why we are trying to propose this new kind of problem setting. Our goal is to detect the failure. We call it failure or the region of interest, whatever, within a certain number of evaluations. And the goal here is the smaller number of evaluations, the better for the budget side. And the more, the better. The more means the more failure regions we find, the better. We are trying to figure out, as I mentioned before, we're trying to find the region that contain these failure specifications. So if we move on from this step, we can further analysis what kind of combinations, what's their relationship that lead to this kind of failure. So instead of doing a global optimization, or we are trying to do more like search for these regions. So we don't want it to get stuck in one area where like cover the global optimum itself, but we also care about to explore the space more to find the other disjoint regions. And the third one is the faster the better, which means we are trying to find the first hitting time for each region, smaller the better, faster. Right? It's like if I can find the first region in the first step, and the second region in the second step, and the third region in the third step, they were perfect. So I don't waste any resource to like run around from over the space to figure out where the regions are. I can get it down within like the number of regions, right? So the motivation for the design is if in each iteration, we can evaluate the location which is of the highest potential to have the best performance. This kind of best performance is related to our goal. What kind of regions design we are trying to evaluate, the evaluation matrix. Then we may be able to achieve this goal. So some formal, kind of formal definition for this problem is each point satisfying this kind of performance we call the specification of interest. And if we can find these points, and then we can define the complete set of this specification of interest as this capital gamma YT. This T is the threshold, the Y is the performance matrix we are interested in. And it contains all the X satisfying this performance. If we care about like the lower side of the, if we define the failure as the lower range of the performance. And we assume it can be written as disjoint sets, right? Like the picture I showed before, like different headers. If you find the, it may not be explicit boundaries. Depends on the space you're working on. But you can certainly write it down as a union of disjoint sets. And these disjoint sets are our goal in this setting. And this number of regions will depend on the threshold. Yes.
Can you something slower percentage that over 8?
You can make it higher dimension. For sure. Like it it just makes it slightly more complicated. Depends on this y-axis. It can be multiple dimension. It just cut the spacing, probably harder to show in a 2D picture, but it can definitely make it like multiple dimension. And each of them are destroying. So given this setting, our goal here is instead of, because we don't have enough evaluations, we don't have enough budget to actually like recover the exact boundaries or the sets. So instead, what we are trying to do here is we are trying to detect representative X. And ideally, they can expand or can represent the regions, like the convex hull of these disjoint regions. Or use the surrogate model we built up for the space to represent the regions. But we are not trying to get like the exact recovery of the set. Does it make sense? Because we don't have enough evaluations, we don't have enough budget to have that deep or detailed description of the space. Does it make sense so far? Yes.
I have a question. Do you know, like, if there are like the back of the region, something you can use to fit out,
So what we know is like we are given some X and some Y to start with, but we don't know anything else. But what we can do is evaluate the Y. If you input a point, I can get you some noisy or like perfect evaluation at that point. But other than this, we don't have enough information to like point the direction for the search. Or actually in our simulation setting, we set the initial points to start like 3 data points, and we set it to be super far away from the regions to see like how long does it take to reach the regions. So this is just a restatement of the problem. And some existing methods regarding this kind of research, not directly, is the failure rate estimation. As I mentioned before, they have kind of strong assumption, and we don't have that enough observations for this really weird case. And there are some structural reliability analysis, or a mathematically closest thing is the excursion set estimation or recovery. They actually care about this set, but they don't. But the goal is more like to recover the set, the full gamma set, given a specific threshold. There is some research regarding the number or the components for these sets, but those things are usually based on a large sample or a large number of observations, so they can have this kind of flexibility, capability to do the recovery or the exact or accurate estimation for the full set. And the next one is the Bayesian optimization. It's not directly related, but it has some pretty nice features we can borrow. And there are actually 2 papers using this method already to this circuit design or this failure rate, region detection problem. But what it did is pretty direct, is they don't care about these disjoint regions. They only care about whether this product pass or fail, or whether this design pass or fail, which means I don't need to know how many regions it has, or I don't need to know the relationship between these parameters and the performance. I only need to figure out whether there's one point, one observations that will give us the performance lower than this threshold. So they reformulate this problem into a global optimization problem and use this Bayesian optimization, which is the framework for the sequential decision making, and to do this failure detection problem. So in the end, it's just global optimization and compare the optimum they find with the threshold and use that to see whether this kind of design fail or pass. And so what we're trying to do is we're trying to still use this Bayesian decision making because we have a black box function and we want it to be a sequential algorithm. And we want to accumulate the knowledge we have found from the newly collected data to update the model. So these fit directly, right, for the Bayesian, even Bayesian optimization, but that's for global optimization. So we cannot directly use that one. So for Bayesian decision making, it's basically follows the following 4 steps. So we need to specify the probability space of all the possible incomes and decisions. And then we need to determine the probability distribution of the outcome given each decision options. And then we need to define some utility function mapping this outcome to real numbers. And then we need to compute the expected utility as a function of given decision and choose the decision that has the best utility function. And basically what we are trying to do is we are trying to model. We are trying to develop a Bayesian framework. And in this case, what we are considering is, let me slightly move. So we are trying to assume that these X are our samples, and this F is the function value, and Y are the real observed performance value. And we assume this Y is coming from this Fx plus arrow, like a regression setting. But this F given X is coming from a Gaussian process regression. And given this Gaussian process regression, we can have the F at each data point. It's a Gaussian distribution. And with certain mean and covariance function. And we assume this mean to be some constant like 0. And the covariance function is given by some kernel function. Pretty standard setting for the Gaussian process regression. And what we are trying to do is, instead of consider some optimization problem, we are trying to develop a sampling distribution for the data points or for the specifications. And given the acquisition or given the performance value, given the posterior distribution of the surrogate model for our performance value. And we use that to design a distribution. Because basically, if you consider in an optimization problem, if we're trying to find like the highest acquisition function value for a certain point, in a probability way, it's like if the point has higher acquisition value, we try to sample them more or easier, right? So these give us some kind of design, or you can consider like the energy-based modeling. We are trying to, instead of doing a direct optimization, we are considering the energy function as part of like exponential of the energy function and do some sampling design. Yes. So it's like the true function. It's like if you're given a parametric model, consider like a linear regression model. everything that can explain by the model, like the bx, the x beta part, is like the fx, like the true value. And what we observe is the y. It's like the true value plus the error terms.
Okay, so the black box function, like we don't also any operate on and that can be.
So in this case, we assume it's a continuous function. That's why we assume it's a Gaussian process regression. It's a continuous function. And we don't assume we know other things. And differentiation, differentiable for the Gaussian process regression as well. But pretty standard assumption, but we don't have too much more information for the function. And we are trying to learn by using this Gaussian process regression, using the kernel to learn the feature relationship to describe the space instead. So we are trying to still use some kind of acquisition function, which means we're using the posterior distribution to come up with some evaluation scores for a certain point. Because we assume Gaussian process, it can be relaxed to some other more general modeling. Gaussian process is just giving you a very easier Gaussian posterior distribution. Everything is going to be Gaussian. And because of this, all the computation for the acquisition or the function we developed to evaluate how good this point is, or how good a certain location is, it's lots of time it's a function of the posterior mean and posterior covariance because everything is Gaussian. And there are definitely some more complicated design, depends on like distributional distance and things like that. But basically, those are trying to evaluate, like if I'm going to evaluate this point, given the surrogate model information I'm getting right now, how much information gain, how much expectation improvements, or how much probability improvements can I get if I'm evaluating this new point? And using that as the criterion to design like where we should evaluate next. I can slightly go back to talk a little more about the acquisition part. So basically the acquisition part is like some criterion. As I mentioned before, it's like the part where we ask ourselves, where should we evaluate next? And the next point, enter this data set should provide us more information about like where the local optimum is or where these disjoint regions locate. So it can be evaluated like the distance between the current evaluation and the threshold, or the distance between the if we evaluate at this point, the performance will be given by the posterior predicted distribution. And this mean distance from the current best observations or from the threshold we are interested in can be an matrix we consider to like evaluate. We try to minimize, right? We try to drag these points to the threshold, or we try to drag this point to the global optimum, or we are trying to push these points to improve the probability, like this point is very likely to locate within certain confidence interval and things like that. So there are different options already designed, and this is like probably the most popular research area in Bayesian optimization. They're trying to come up with different acquisition design. So the points or the sequence they observe is going to follow certain patterns they're interested in. And basically this design is trying to balance two parts, the exploration and exploitation, which means Now we already observed something. If we just focus on the parts we have information already, we can get certain performance with very high confidence or low uncertainty because we already know what's going on like around these points we observed. But also, we want to explore the space more. But exploring means we will need to go to the area where we have less observations or high uncertainty. So it's kind of a trade-off problem for this kind of design. We want to balance this one, and they come up with different design, like the lower confidence bound or the expected improvement focus on like how much improvement you can get expectational wise from the current observation and the predict posterior mean, or the yes.
Which one is
This is the current best observation, and this is like the some new points you're going to evaluate, and it will have some effects.
oh, so both are the caution process.
Yes, but this is observed already. If you have like a no noise situation, then it's observed.
Oh,
Right.
so this is a value on the.
Yeah, it depends on whether you observe the noisy or like no noisy version, but yeah, something like that. And similar thing as follow. It's like how likely this point is going to have performance lower than the current behavior. Or you can change this to like compare to the threshold, how likely it's going to have the performance lower than this threshold and things like this. And this entropy search is like the distributional distance I talk about. There's some reference distribution they propose, and they are trying to drag this observation to this reference distribution. And but
Plus the now valuation of your working process information, and at the end you are getting pretty much the same.
so there's no guidance, like there's no rule to choose like which one is the best. But they may have different performance, especially when you have smaller observation. You can imagine, right? If you have large observations, a large number of observations, the Gaussian process will be pretty similar, and which lead to other posterior distribution and things like that. So when you are getting more, they are going to perform similar. But if you have limited, they will probably point you to like different points. But they also they basically are trying to evaluate this kind of distance or the goodness of the point through different matrix, expectation or the probability or something else. So yeah. And for the last one, it will be harder and there will be lots of numerical computation instead because you're going to compute something you cannot observe. So they're trying to the computational wise is more complicated. But basically that's the idea. They're trying to come up with some function to evaluate the goodness of the point. So you can use that to do optimization or to design some sampling function to guide the search. So the overall performance will kind of move to the direction you want. It's like the experimental design problem. How to like consider like how to assign those points in the space so you can know the specific regions better. Yeah. So a very so the full algorithm for our proposed method, it's like we're trying to still use the surrogate model, still use the Bayesian framework, but we're trying to propose a sampling distribution at each step instead of doing some optimization. And then we're trying to incorporate some other selection steps in our scenario. And then we can add those samples to the data set and update the model still. And for the proposed distribution, we consider the current acquisition function. We also propose some new acquisition function. But the main idea is if we are trying to optimize the acquisition function, then we want this point to be more likely to be sampled if it has higher value of acquisition values. So we can use this kind of performance or observations to design the sampling distribution. And because X doesn't really have a distribution, it's manually proposed distribution, right? Or we can also build it in a very fully Bayesian way. Like you assume there's a distribution for X as well. Then you can propose the acquisition function or this sampling distribution as just like a posterior distribution, given the current surrogate model and the data you observed. But anyway, so the proposed sampling distribution is going to proportional to some function of the acquisition function. And the good thing about this kind of design is if we have a sampling distribution, it will be easier to get multiple points. You don't do parallel optimization for like a multimodal. It's very likely to be multimodal if you have a very complicated acquisition function. So if you are trying to get multiple data points at one batch, at one iteration, people just do parallel optimization and get different points. And then they can add those points back to the data set. But with sampling, that's basically how it looks like. It's a acquisition guided part and the pre-screening part. And we don't know the constants, but there are like lots of algorithms developed for not knowing the constants, only knowing the proportional part, right? So we choose some Monte Carlo algorithms to do the sampling part. They can be multiple. And then we also design some different easier acquisition function to do, but I will skip it for now. Just talk about some motivations. And the reason why we choose sampling is we are trying to get multiple suggestions at a time. And also we try to use the randomness brings in by sampling to jump out of the certain regions. Because Bayesian optimization is designed for global optimization. So the performance itself will be very likely to start in one region. And we are trying to use this kind of sampling performance to push them to get out of the regions. So we can get like performance from different area of the space, but also still with certain guidance, just adding some randomness. Also, because this kind of design, we can use different criterions or with the pre-screening parts. It means we don't need to do a very complicated optimization problem because we already have use sampling, we can get a pool of candidates and then we can do selection based on these candidates, which is like the pre-screening part or the indicator function for the selection of these candidates to satisfy the distribution. And so this will simplify the computational complexity brought by the complex acquisition function. And also this can add more exploration in the early stage. And this motivation also comes from the energy-based model, as I mentioned before, or the entropy search for the distributional kind of distance. And also there are some paper study the efficiency efficiency in optimization given by sampling and optimization. And under certain conditions, sampling can be more efficient, especially for some like multimodal, but of course with some conditions for the covariance structures. And also connected with the strategic agents background. So that's basically the whole model setting and what we proposed. And for simulation, we tried this proposed method, and we compare with like the uniform random sampling and some classic Gaussian process-based optimization, Bayesian optimization, and we choose different acquisition function like the expectation of improvement and the probability of improvement, and upper confidence bound or low confidence bound, and the Thompson sampling. And also the last one is the tree structured Pearson estimator. It's also one type of Bayesian optimization, but it proposes in a slightly different way, but still one kind of Bayesian optimization. And the initial data set is composed of specifications with response far away from the ideal regions, as I mentioned before. And we do like 30 simulations. And these are the matrix we considered. As I mentioned before, we want it to be as fast as possible, as more as possible. And so we consider the time, the first hitting time for each region, and also the average rate of detecting the ice regions, and also the average number of regions of interest or specifications of interest until the nth evaluation. And the second one is because for some functions, we don't know the total number of regions. We cannot find, like for some function pretty bumpy, you may have hundreds or thousands of like regions. So for this case, it would be really hard to know the specific number directly. Then that's where we just use the number of specifications. And also we consider the average length of or the area of the convex hull generated by these points within the regions. And the last one is still the optimum performance for these regions. And we consider, I just show some illustrated pictures that we can consider. Start from one dimension. If it's a global optimization, we just need to find this point. But now I set this threshold to be negative 0.5, I think. So then we have two regions of interest to detect instead of just one. And this one, these two are like two-dimension function, which has 3, given the threshold I set it to be, and this has like 25. And the last one is the very bumpy scenario I talked about, and we consider like higher dimension, but only show a two-dimension thing. And that's where we will report the like specification of interest, number of specification of interest. And I'm going to just go through the results pretty fast. So basically, the left-hand side, it's for the Bayesian optimization, and the right-hand side is for the sampling algorithm. And this is showing the number of regions detected by different algorithms, and this is the same. But this one is for the one-dimension function, and this one is for the second two-dimension function. And basically, we can see that, as we mentioned before, the choice of acquisition function will affect the performance a lot, especially when you only have limited observations. And also, not all of them can find like two regions. Some may get stuck in a local area because we start from some area far away from the regions of interest. And relatively similar performance, even though choosing the same acquisition functions for sampling methods, they eventually reach to like the 2 for all of these methods. and similar performance showing up here as well. And we also consider, this is for the 25 local regions we are trying to find algorithms. I'm cutting off at like 120 performance for different algorithms. And that's how much they can detect based on this like preliminary results. And also this is the time we can see the sampling algorithm for the first detection time. Average first detection time is slightly shorter for each of these regions. You can see from the slope change for these regions. And there are more where we consider basically if you change the threshold, the difficulty level of the problem change as well, because you will get smaller and smaller regions. Eventually you will get to like the global optimum or local optimum problem where you can only detect one point, right? So this is basically showing that it has more flexibility even when the problem gets harder. Of course, it will have more less ideal performance, but it can still detect something compared to the pure Bayesian optimization itself. And we also have an example for a circuit design, but they have similar information. I think I will just skip here. So basically, that's the direction I'm interested in, like an efficient regions of interest detection, which can be applied to multiple scenarios like hyperparameter tuning. We also did some examples where basically we're trying to see how these different parameters can contribute or affect the performance we're interested in, like the classifier acquisition, the classifier performance for like image or something like that. And well, this also opens up some projects we're currently doing. As I with a certain budget constraint, how can we design an algorithm to detect as many of these regions of interest as possible? And this can be connect to like the experimental design for sure, or some QMC idea can be used here as well. Like how can you push those points to some like the compressed QMC, where you don't have a regular space, but you can kind of assign the points more in those specific area. Consider this as calculating some expectation from the conditional distribution instead of like assigning the points to all the space to do the calculation. And yeah, so there are some ongoing works as well. So that's pretty much everything I want to present. And yeah, thank you for your attention. I think that's yes.
So I'm understanding like for identifying like the different types of like failure rules, you have a specific set of parameters that you already kind of like set things up to look for.
No.
Oh, it's not.
No, it's just whatever given. And you can set the threshold yourself. Depends on how good or what's your like quality control level. And then you have some observations, which can be a few, like less than 10 to start with, or less than, for the simulation, it's like we only have 3 at first, then we accumulate data based on this guidance.
So a set of certain to work exactly in the way you wanted to train, like, or use that as like kind of like a set to show like what to look for in a good set, and then have it run on the you haven't and don't know if there are any failures into see if there are any there.
Do you mean try to incorporate some prior knowledge, knowing for the simulations or the case I'm showing here, we didn't do that. We just have the data and have the threshold. That's it. But you can definitely do that if you already have those information to like shrink the space you are trying to explore. Right. Yes. You can do that. Actually, there's some like Bayesian tree Gaussian process or something like that. Like you kind of split the space using some kind of algorithm. You can use KNN, use some clustering method as well, but it's not done yet. But you can do that to like improve the search path. Yes.
So once you understand that those are like your method looks like, am I understanding that correctly? The only way to prepare you to be going search away from the region is the randomness example, or do you have any mechanism to explore?
Oh, so we also propose some algorithm, the acquisition function that push your next evaluation point to be away from the current observed regions or observed points. But if you're using the existing acquisition function, they don't do that because they are for global optimization. So they don't need to push things away from each other. Does it make sense?
Yeah, conceptually, I would say it's because
Oh, it's like you consider the location of the next evaluation point and in your acquisition function, it's like you haven't explore evaluate at that point yet, but you can use the distance of that specific point and the current observations to like weight the acquisition, right? Like push if it's like too close, then I don't want it. I set it to be like a really low if I try to like find the maximum value. Anything else? Otherwise, that's the end, I guess. Thank you.